In this module, you will learn about the types of brain responses that are measured by MEG. Specifically, we will discuss evoked and induced responses and some of the caveats to collecting and analyzing quality data. During the course of this presentation, we shall provide insight into what is spontaneous neural activity, what are evoked responses, when averaging evoked response trials, why is the timing important, what are induced responses, why are time frequency representations better suited for analyzing induced responses. Brain activity recorded by MEG can be categorized into three types. Spontaneous brain activity is recorded when a subject is doing nothing. The subject is typically instructed to remain still with eyes open or closed and to think of nothing. Analysis includes evaluating resting state activity, connectivity between brain areas, or for studying abnormalities such as in epilepsy. Steady-state, ongoing responses require modulations of sustained oscillatory brain activity such as frequency encoding or tagging of stimulus or regression with behavior parameters. These responses require repeated experimental trials of longer duration. Analysis of steady-state responses can include narrowband power modulations, functional connectivity, and phase lags. Event-related responses require repeated experimental trials of shorter duration. Often, there are many trials and multiple conditions. The aim is to detect stimulus-related evoked or induced activity. Analysis of event-related responses can include metrics of amplitude, latency, and event-related oscillatory bursts. During this module, we will focus on these event-related responses. Here, we illustrate the difference between spontaneous and evoked responses. Spontaneous measurements can be done in long extended periods when a subject can remain still or during sleep studies. More often, these measurements are done in shorter blocks, possibly letting the subject rest between the blocks. For evoked studies, there can be a range of stimuli. For example, sounds, touch, images, video clips, smells, or a combination of these. During stimulation, the subject can be asked to perform tasks. Examples include attending or ignoring stimuli, detecting and reacting to stimuli, for example by button press, detecting and counting stimuli, imagining or observing and or imitating, for example with facial gestures. Additional behavioral responses can be required, such as limb or finger movement and speech. Evoked responses are then recorded and optionally extracted as epochs according to the timing of stimuli, tasks, or responses. Those epochs can be averaged online or offline together with other signal processing to improve signal-to-noise ratio, especially if offline interference suppression and head movement compensation are needed. The example here shows some extracted and averaged epochs denoted by the yellow shaded areas, and one epoch rejected from the average because of artifacts shaded by red. In order to design efficient functional neuroimaging experiments, one needs to consider the dynamics of the measured neural variable and the rate at which this variable can be sampled. The fMRI bold signal reflects changes in the oxygen consumption, which lags the neural activation by 5 to 10 seconds and varies slowly over a period of several seconds. This illustration shows the brain responses when the stimulus duration is short, 200 milliseconds, long, 2 seconds, or sustained, 15 seconds. A prominent bold effect is obtained only with stimulation persisting for several seconds. In contrast, MEG signals are a direct measure of neuronal activity and can be sampled at very high rates. Fast evoked responses are primarily elicited by stimulus onsets and offsets, with possibly a relatively weak sustained response. Ongoing oscillatory activity seen by MEG, mainly alpha around 10 Hz and mu around 10 and 20 Hz, may undergo suppression and rebound modulation, whose time course is more comparable to that of bold. In gamma band responses above 30 Hz, the oscillatory activation during short and long stimulus is enhanced, but returns to baseline level when the stimulus is switched off. During a sustained stimulus, the gamma oscillations start to gradually attenuate. Let's consider the evoked responses more carefully. Evoked responses are neural activations that repeat from trial to trial, at the same time phase-locked to stimulus or task onset or offset. Evoked responses are typically detected within the first second from the stimulus presentation or execution of the task. The earliest salient responses, for example those of shortest latency, are typically short-lasting and tightly locked to the stimulus. They yield sharp responses even when averaged across multiple trials. The longer latency responses tend to progressively increase in duration and are likely to exhibit more physiological jitter with respect to the stimulus timing. When averaged, they appear as sustained responses with slow fade-in and fade-out phases. Naming of the MEG response waves follows the EEG literature, N for vertex negative and P for vertex positive responses, followed by the latency in milliseconds, for example N100 or P300. The suffix M is often used to emphasize neuromagnetic responses, for example N100M. Analysis of evoked responses typically includes averaging epochs. Evoked single trial responses may be detectable, but often have a poor signal-to-noise ratio, or SNR. To improve the SNR and allow for accurate detection and localization of the underlying sources, tens or hundreds of trials are collected to yield an average evoked response. Averaging improves the SNR by the square root of n, where n is the number of averaged trials. This holds true providing that the noise in the data is temporally uncorrelated from trial to trial, meaning it is not time-locked to the stimulus. Therefore, the epochs should have stimulus-locked activity and uncorrelated noise to successfully recover the underlying response signal. It is recommended to have about 100 accepted trials per condition, with a realistic estimate of 15 to 20% of the trials contaminated by eye blinks or other types of artifact signals. One such rejected epoch is indicated by the red column in this example. Here is an example of improved SNR thanks to averaging. The example shows the evoked response to electrical stimulation of the median nerve at the wrist. On the left is the MEG signal from a single planar gradiometer channel above the S1 hand region of the brain. Here, N is the number of trials that are averaged. You can see that with increasing number of trials in the average, there is a smoothing or a decrease in uncorrelated noise. It is also important to point out that the earliest responses of N20M and P35M are already apparent in the single trial response, but that their amplitudes decrease slightly when more trials are presented. Several factors are at work here. The response amplitude often decreases with frequent presentations of the same stimulus, but also the biological noise may increase with a prolonged measurement because of subject fatigue, like frequent eye blinks, muscle artifacts due to neck tension, or movements. Together, this means that the SNR improvement in practice is somewhat worse than predicted by the square root of n formula. Let's consider these characteristics for a moment. Habituation is a decrease in response to a stimulus after repeated presentations. The interstimulus interval, often referred to as the ISI, should be long enough to allow the neural responses to return to the pre-stimulus baseline, ranging anywhere from 200 to 1000 milliseconds. So, faster stimulation and shorter ISI yields more trials in the recording, but also generates more habituation and signal decrease. Depending on the experiment, consecutive stimuli typically have a range from 1 to 3 seconds. Randomization of stimulus types and ISI lengths is recommended to improve vigilance and reduce habituation. In an oddball paradigm, the sequences of repetitive stimuli are interrupted by a deviant stimulus at an infrequent rate. The reaction of the participant to this oddball stimulus is recorded. The resulting mismatch negativity is an evoked response which detects sensitivity to a non-predictable change in sensory input. When averaging many trials, the exact timing of the stimulus presentation is very important. During the stimulus production, there can be a variety of delays. This means that the stimulus and the corresponding event trigger may not be perfectly synchronized. We refer to this as stimulus trigger jitter and can cause smeared evoked responses. The picture on the right demonstrates the effect of stimulus trigger timing accuracy on the averaged signals. The evoked response to the electric median nerve stimulation with precise timing is shown in the blue curve, and the red trace shows the result when 20 milliseconds of random jitter is present. As you can see, this sloppy timing destroys the fast components of the response. Besides technical jitter, physiological jitter can also produce similar effects. It may be necessary to perform single trial analysis to reveal physiological trial-to-trial variations in amplitude and latency. The reliability of MEG responses can be verified by repeating the experiment and comparing the results. Physiological factors, technical aspects, inaccurate co-registration of the MEG and MRI coordinate systems, and uncompensated head movements can result in displacement of the source on the MRI anatomy. When the underlying neural sources are strong and exhibit simple field patterns, they are easy to model. In those cases, co-registration procedures are responsible for most of the localization errors. When the experiments are performed carefully, repeatability of localizing such sources can be quite good, in the range of a few millimeters. In this example, 8 MEG measurements performed on the same subject over a period of 2 years all yielded consistent responses to auditory stimulation. The equivalent current dipole locations of the N100M, estimated from the responses, are shown as blue dots on the structural MRI of the subject. The corresponding source waveforms vary slightly in amplitude, whereas the peak latency remains similar. Induced responses are event-related modulations of cortical rhythmic activity. Often referred to as stimulus-induced or task-induced, these responses are time-dependent variations of the amplitude of oscillations within a frequency band of interest. They may reveal effects that occur systematically across trials, but are less strictly time-locked to the stimulus or task timing. Unlike evoked responses, the oscillatory signal itself is not phase-locked to the stimulus presentation or task, and these components typically vanish in the time domain when averaging. This example shows the frequencies of alpha and mu rhythm in gradiometer channels in a MEG recording. The sensor array is shown from 2 viewing angles, back and right. The 10 Hz alpha waves originate from parieto-occipital junction, while the 10 and 20 Hz mu activity arises in the Rolandic region. Alpha is strongest in the posterior MEG sensors when the subject has eyes closed, while mu is strongest in the sensors over the sensorimotor cortex when the subject is totally relaxed and not doing any movements. Alpha rhythm is abolished by opening the eyes, and mu rhythm vanishes during hand movements. Induced responses are used to characterize changes in ongoing brain activity in response to a stimulus. Since induced responses are not phase-locked to the stimulation like in evoked responses, the phase information must be removed before averaging. Wavelet-based approaches are generally used in time-frequency representations of amplitude or power. An example of time-frequency representations of a magnetometer channel signal from visual stimulation is shown here. It represents the calculated instantaneous signal power by Morlet wavelets. The result shows both alpha suppression and gamma enhancement. Another popular approach is temporal spectral evolution. This characterizes absolute rather than relative power changes with respect to a baseline. These two techniques are not included in MEG analysis software and are not intended for clinical use. This information is for research only. The manuals that come with your MEG system contain important information about using your MEG, including safety warnings. You must familiarize yourself with this material before operating your MEG.